When NASA aimed its instruments at the interstellar object known as 3I/Atlas, nothing suggested it would rewrite the laws of physics. But once a quantum AI was unleashed on the images, everything changed. It detected signatures no astronomer expected, a tail pointing toward the sun instead of away from it, and motion that doesn't match any known comet. This is only the third interstellar object ever seen passing through our solar system. Yet it may be the strangest of them all. What the AI uncovered goes beyond odd data points. It hints at a mystery that even NASA's brightest minds can't explain. If the universe is sending us a warning, 3I/Atlas might be it. Before we dive in, make sure to subscribe and turn on notifications, because the mysteries of the universe are only getting stranger. Dust streaming toward the sun from an interstellar comet is not supposed to happen. Yet, that's exactly what the latest NASA images of 3I/Atlas reveal. A plume of particles stretching in the wrong direction, defying the basic rules of comet physics. Normally, sunlight pushes dust and gas away, forming a tail that points directly opposite the sun. That's radiation pressure in action, a force so predictable it's used to steer spacecraft. But here, the dust clings to the sunward side as if gravity and light are playing by a different set of rules. Spectroscopic scans add another layer to the puzzle. Astronomers look for telltale signs, specific fingerprints in the light spectrum that reveal what a comet is made of. In almost every active comet, you'll find clear markers: cyanogen, diatomic carbon, and other volatile gases glowing at specific wavelengths. These are the chemical signatures of a comet, waking up as sunlight hits its icy core. But in the first weeks after discovery, 3I/Atlas showed none of these. No cyanogen, no diatomic carbon, not even faint traces. The spectrum was nearly blank where it should have been lit up. Think of it like watching a campfire that burns hot but produces no smoke. The dust is there, obvious, even dramatic in the images, but the usual chemical evidence is missing. It's as if the comet is venting material in a way no one expected, or from a composition that doesn't match anything seen in the solar system. Only months later, as the comet closed in on the sun, did a faint whiff of cyanogen finally appear. Late, weak, and still out of step with the dust activity. This combination, dust streaming sunward, a coma without its usual gas, and a delayed chemical response, has left researchers searching for answers. Some point to possible surface crusts hardened by billions of years in interstellar space, shielding inner ices from the sun's heat. Others wonder if the comet's spin axis is locked in just the right way to expose only certain regions. But the basic contradiction remains: a sun-facing tail, absent volatiles, and a profile that fits neither comet nor asteroid. For now, the physics just doesn't add up. NASA's imaging teams faced a challenge unlike any before. Calibrating the stacked exposures from the Atlas survey, they traced the faint moving point of 3I/Atlas frame by frame. Each pixel carried the weight of cosmic history. The resulting data pointed to a nucleus no smaller than 0.3 kilometers and possibly as large as 5.6 kilometers across. That's not just big for an interstellar visitor, it's enormous. For context, 1I/Oumuamua, the first known interstellar object, was likely less than 200 meters long. 2I/Borisov, the second, measured about a kilometer. 3I/Atlas could be 5 times that, or more. Only 3 confirmed interstellar objects have ever been recorded. To find one this large, this active, and this close is statistically staggering. The odds of randomly detecting such a giant, given the survey's sensitivity and the volume of space it covers, are vanishingly small. Most interstellar objects slip by unseen, lost in the glare of distant stars or too faint for even the largest telescopes. Yet here, the data chain is clear. From initial Atlas discovery to follow-up with Hubble and JWST, every image confirms the same immense active core. The object's brightness, measured across multiple nights and instruments, rules out small debris or a swarm of fragments. This is a single monolithic body, an ancient traveler older than our Sun, carrying material forged in a different star's disk. Astronomers tried to model how such a large interstellar object could cross our path. Simulations suggest the odds are less than 1 in a million for a random ejection from another system to land one so close to Earth's orbit. The scale alone raises questions about what else might be lurking in the dark, undetected. This is not just another comet. It's a statistical outlier, a cosmic heavyweight that defies the usual odds. The numbers demand attention, but the real shock comes from where it's going next, a path that carries it dangerously close to several major planets, one after another. When scientists at NASA and JPL ran the numbers, they began with a straightforward question. Where exactly is 3I/Atlas headed? The answer revealed a journey through the inner solar system that's anything but ordinary. On October 3, 2025, the comet will skim past Mars at just 0.19 astronomical units away, only 28 million kilometers. That's close enough for even the most cautious models to flag it as a near miss, especially for an interstellar object racing in at 58 kilometers per second. Barely 4 weeks later, 3I/Atlas reaches its closest point to the Sun, whipping around at its peak speed of 68 kilometers per second. Then, on November 3rd, it sweeps within 0.65 astronomical units of Venus. To put that in perspective, it's actually inside Earth's orbit, an area rarely visited by any comet, much less one that comes from beyond the solar system. These distances aren't just raw figures. They're the result of a delicate gravitational dance between the Sun, the planets, and the comet's own immense speed. Each encounter demands new calculations and introduces new variables. The principle of gravitational assist, a technique spacecraft engineers carefully plan years in advance, is at play here too. As 3I/Atlas brushes past Mars and then Venus, each planet's gravity tugs at it, shifting its course in subtle but noticeable ways. For a spacecraft, that kind of maneuver is deliberate. For a natural body like this comet, the odds of such a precise sequence happening by sheer chance are incredibly slim. The orbital data paints the full picture. Passing Mars at 0.19 astronomical units, then Venus at 0.65 astronomical units, all within just 1 month, while holding a retrograde tilt of only 5 degrees relative to the ecliptic. Every leg of this journey has been charted in exacting detail. The timestamps, the speeds, the distances, and the precise angles between the comet's path and the planet's orbits. The figures are straightforward, but the pattern they create is anything but expected. It looks less like randomness and more like a carefully threaded route, almost as if the comet is slipping a needle through the inner planets. Gravitational assists explain how a planet's motion can speed up or redirect a passing object. For 3I/Atlas, the effect is minor but measurable. Its trajectory bends slightly at each close pass, though the overall path stays hyperbolic, an open arc that will eventually sling it back into interstellar space. What makes this striking isn't the physics, but the timing. Mars first, then Venus, in such a tight sequence of space and time. Mapping these encounters demands precise knowledge of where the planets are, how fast the comet moves, and the pull of the Sun's gravity, all verified independently by teams using NASA's Horizon system and JPL's DE441 planetary data. The comet's course through the inner solar system is now firmly locked in. The laws of motion and gravity ensure these encounters will happen exactly as predicted. What no one can say for certain is how likely it is for such a perfect sequence to occur randomly. What is certain, though, is that the voyage of 3I/Atlas is unlike anything astronomers have ever tracked before. The raw figures, 58 kilometers per second, October 25th, November 25th, distances measured in tens of millions of kilometers, tell the story of a cosmic traveler on a path that resists easy explanation. As the comet streaks toward its next planetary encounter, the stage is set to confront just how improbable this trajectory really is. Probability in astronomy is rarely this unforgiving. When Adam Hibbert and Abraham Lowe crunched the numbers for 3I/Atlas's journey, the outcome startled even veteran orbital dynamicists. Using Monte Carlo simulations, billions of randomized test runs, they asked how often an interstellar object with similar speed and tilt would pass as close to Mars, Venus, and Jupiter as 3I/Atlas is about to. Out of hundreds of thousands of generated paths, fewer than 0.005% lined up with this exact sequence. That's about 1 in 20,000. For perspective, those odds are comparable to choosing a single specific second out of an entire week. This goes far beyond simple coincidence. Each planet sweeps through only a small slice of its orbit at any given moment. For a comet on a hyperbolic path to slip within 0.19 astronomical units of Mars, then 0.65 astronomical units of Venus, and later graze Jupiter's orbit, all inside a few months, requires a chain of timing and geometry that borders on impossible. In the simulations, the entry time was left free while the velocity and inclination were fixed, letting the planets rotate naturally around the Sun. Most trial runs missed by vast margins, tens or even hundreds of millions of kilometers. Only a rare handful mirrored the real sequence. Lowe's team used an analogy that makes the point vivid. Imagine throwing a dart blindfolded at a spinning globe, hitting 3 tiny cities in perfect succession, with the globe rotating between each throw. The odds don't just add up, they multiply, collapsing with every required encounter. The simulation results looked like a vast field of near misses, with 3I/Atlas's actual track standing alone, a single bright dot in an empty patch of statistical space. Some argue that with enough interstellar wanderers, even events with odds of 1,000,000 to 1 are bound to appear eventually. But the catch is that we've only ever seen 3 of these visitors, and only 3I/Atlas has taken this extraordinary route. The improbability isn't just a mathematical curiosity, it challenges the view of the solar system as a passive backdrop for random interstellar traffic. When the numbers drop this low, astronomers begin to suspect something is missing in the model, or wonder if there's more than mere chance involved. That's where the next step begins, unleashing AI to probe the data for patterns beyond human intuition. Quantum AI systems excel at spotting signals hidden in noise. When they sifted through the entire archive of Atlas survey images for 3I/Atlas, the first anomaly wasn't its brightness or shape, it was rhythm. The AI's period detection algorithms, running thousands of parallel checks, latched onto a repeating cycle in the comet's light curve. Not random flicker, not the slow dimming of dust moving away from the Sun, but a sharp, reliable periodicity. Each pulse arrived right on cue, like a heartbeat buried in the static. Statistically, The signal cleared every threshold researchers set. The probability of such a rhythm arising by accident in a chaotic, dusty environment fell below 1 in 10,000. Traditional analysis would have struggled here. Human astronomers might scan dozens of light curves in a night looking for obvious dips or rises. The AI, by contrast, processed all available photometric data at once across filters, nights, and telescopes, testing every plausible period from minutes to days. It's the computational equivalent of listening to 100 orchestras at once and picking out a single violin's repeating note. This kind of parallel processing is where quantum-inspired systems shine. They can sift through mountains of raw data, isolating subtle, consistent changes that would blur together in a manual review. The periodicity wasn't tied to known comet behaviors. It didn't match the expected spin rate for a nucleus this size, nor did it line up with any known orbital resonance. The AI flagged it as a genuine anomaly, something real in the data, not an artifact of the instruments or a trick of background stars. Cross-checks with independent datasets, including Hubble and ground-based photometry, confirmed the same pattern. The signal was there, night after night, persisting even as the comet's overall brightness changed with its distance from the Sun. Some researchers liken this to finding a metronome ticking inside a storm. The AI's ability to pull order from chaos, to recognize a hidden clockwork in the glare and dust, gives astronomers a new edge. It's not just about seeing more, it's about seeing differently. With this kind of pattern in hand, the next step is clear. Test whether the periodicity ties to a physical property, a structural feature, or something even stranger. But as the algorithms kept crunching, another anomaly surfaced, one that pointed to a force acting on 3I/Atlas that standard models couldn't explain. Acceleration data from the Atlas survey brought an unexpected twist. When researchers mapped the position of 3I/Atlas over weeks, the numbers didn't quite line up with what gravity alone would predict. The comet's path showed a persistent, measurable deviation, tiny but unmistakable. The calculated acceleration was on the order of 10 to the -7 meters per second squared, far above the level expected from radiation pressure alone for an object of this size. At these velocities and distances, sunlight should have a predictable effect, pushing dust and gas away in a steady outward drift. Yet, the observed acceleration pointed slightly off that line, as if a faint invisible hand was nudging the comet sideways. The first explanation on the table was outgassing. When sunlight heats a comet's surface, jets of vaporized ice can act like miniature thrusters, gently steering the nucleus. This process has explained similar anomalies in past comet trajectories, including the famous case of 1I/Oumuamua. But here's the catch. The usual signatures of outgassing, spikes in cyanogen or diatomic carbon, sudden brightening, or jets visible in high-resolution images, were missing or appeared too late to account for the early acceleration. The force was present before any clear sign of active jets. That left two camps. Some scientists argued for a crust of hardened material, perhaps baked solid during billions of years in interstellar space, which could mask or delay normal outgassing. Others looked at it with more exotic theories. One proposal, still hotly debated, is that radiation pressure from sunlight could be stronger than expected if the nucleus is unusually thin or reflective, almost like a natural light sail. If that's the case, the physics of this object would be unlike any comet seen before. A possible interpretation floated in recent workshops is that a combination of faint outgassing and radiation pressure might be at work, modulated by the comet's spin and surface properties. But so far, no single model fits all the data. The quantum AI flagged the force anomaly as a genuine outlier, not a statistical fluke. The result? A growing list of unanswered questions and a debate that reaches well beyond the usual boundaries of comet science. With each new frame, the mystery deepens, and the search for an explanation moves one step further into uncharted territory. Standard comet science offers a checklist of possible explanations for the three I/Atlas anomalies. Outgassing jets of vaporized ice acting like tiny thrusters have long explained small deviations in comet paths. When sunlight heats a comet's surface, ices sublimate and vent through cracks, sometimes pushing the nucleus in unpredictable directions. For most comets, these jets leave clear chemical traces, spikes of cyanogen or diatomic carbon, brightening events, even visible jets in high-resolution images. If 3I/Atlas followed this script, the delayed gas signatures and odd acceleration might fit a pattern seen before. Shape plays a role too. A stretched-out or lumpy nucleus can wobble as it spins, catching sunlight unevenly and heating in patches. That imbalance can spark bursts of gas, making the comet zig and zag as it heads toward the sun. Some scientists point to 1I/Oumuamua, which showed a puzzling acceleration later tied to outgassing, even though no gas was directly spotted. Technical quirks also deserve attention. Things like stacked exposures, background cleanup, or calibration slip-ups can fake faint rhythms or phantom accelerations. That's why astronomers double-check with independent telescopes and data pipelines, hunting down these ghosts of instrumentation. All of these standard explanations are being tested against the evidence. Outgassing has been modeled with different spin rates and nucleus shapes. Possible photometric artifacts are compared across instruments and observing teams. Yet so far, none of these common scenarios explain the steady sunward dust, the chemical delays, or the measured push in motion. The puzzle hasn't cracked, not because no one's trying, but because the usual answers just don't fit. A handful of visionaries are now asking, what if 3I/Atlas isn't just a random oddball, but a clue to something stranger hiding underneath? Some have suggested that instead of a chunky snowball, the nucleus might be shaped more like a thin sheet, perhaps even resembling a natural version of a solar sail. In that case, sunlight itself could act like a gentle engine, pushing it in ways that mimic artificial propulsion. It sounds far-fetched, but the numbers line up with how an ultra-thin, reflective shard would behave under radiation pressure. Another possibility involves exotic ices, rare substances like nitrogen or carbon monoxide, which barely survive in the inner solar system. If such ices hide beneath a crust, toughened by eons of radiation, they might only vaporize under certain temperatures or sunlight angles. That would fire off jets unpredictably, creating the odd acceleration and delayed chemistry we're seeing. In this view, 3I/Atlas could be a relic from a planet-forming disk that looks nothing like our own. And then there's the debris field idea. Some theorists suggest we might not be looking at one comet at all, but a shard of a much larger body shattered long ago, now drifting with an invisible fleet of interstellar fragments. If that's true, 3I/Atlas may just be the first piece we've spotted. An iceberg tip carrying clues about its long-lost parent world. None of these scenarios can yet be proved, but each one stretches the mystery further beyond the ordinary, nudging us toward the edges of what might be possible. On July 1st, 2025, NASA's Atlas survey confirmed the discovery of the third known interstellar object, 3I/Atlas, measuring up to 5.6 kilometers across. Close-up images revealed three unsettling details. A dust tail pointed at the sun, without the usual comet gases, a massive and unusual core, and a path weaving past Mars, Venus, and Jupiter, with odds of that alignment below 0.005%. Quantum AI tools picked out hidden repeating signals in its light curve and flagged an unexplained acceleration. The usual suspects, outgassing, odd shapes, or technical errors, fall short of explaining everything. Exotic ideas have been floated, but none perfectly fit the data. To make things even more intriguing, key files, raw AI outputs, and spectral models remain either restricted or unpublished. What scientists do agree on is that 3I/Atlas defies the standard playbook for interstellar visitors and stretches the limits of what we think we know about solar system physics. As fresh data trickles out, the mystery holds firm. For now, 3I/Atlas pushes us to rethink what it means when objects arrive from deep space, and reminds us that the universe is still very good at keeping its secrets.